Hello, and thank you for watching our final presentation. This is Sentry, the smart locking and tracking system for bicycles. Our team is comprised of 4 members: Andres Garcia, Derek Amin, Russell Ridley, and myself, Ryan Baumgartner. Together, we are 2 electrical engineering majors and 2 computer engineering majors.
One of the biggest challenges on university campuses is bike theft. Many students rely on bikes as their primary mode of transportation, but unfortunately, bike theft is a recurring issue that makes people hesitant to use them. This isn't just about the loss of a bike, it disrupts daily routines. If a student's bike is stolen, they might be late for class, have to find an alternative mode of transportation, or even avoid biking altogether in the future, which affects sustainable transportation habits. Right now, traditional bike locks don't provide proactive security. They only act as a physical barrier, but if someone cuts the lock, the owner has no idea until they return and find their bike missing. There's no immediate alert, no tracking system, and no way to recover the stolen bike quickly. But with advances in IoT and smart technology, we can change this. We now have the ability to integrate real-time alerts, GPS tracking, and remote monitoring, making bike security much more effective. That's where our smart bike lock, Sentry, comes in, providing a smarter and more secure way to protect bikes. Sentry is a high-tech bike locking and tracking system designed to provide both security and convenience. It features NFC and BLE for secure unlocking, allowing users to tap their phone or use the mobile app. GPS tracking enables real-time location monitoring, helping users track their bike if it's moved or stolen. With cellular connectivity, the system sends instant alerts when tampering is detected, ensuring owners are notified immediately. An audible alarm deters theft by drawing attention, while the mobile app provides full control over unlocking, tracking, and security notifications. By combining these smart technologies, Sentry offers a proactive approach to bike security, making theft prevention and recovery more effective. The primary goal of Sentry is to enhance bike security using NFC, GPS, and cellular connectivity. It prevents theft through tamper detection, audible alarms, and instant alerts, while real-time GPS tracking assists in bike recovery. A user-friendly mobile app allows for tracking, unlocking, and monitoring, ensuring ease of use. The system is designed with durability and outdoor resilience in mind. For our objectives, we focus on implementing the core features that bring our smart bike lock to life. First, we aim to develop a mobile application that is user-friendly and intuitive. We also integrate NFC technology, allowing users to unlock the bike lock using their smartphones. To keep users informed, we incorporate a notification system that pushes alerts directly from the mobile app. Finally, we included real-time location tracking so users can monitor their bike's location at any time.
In order to meet our goals and limitations, we need to define the required specifications. The reason behind this is that we need to have set parameters of goals that we want to achieve with our system. Since our product is going to be used daily by consumers, we wanted a refined product that the consumer can trust and so be in charge of keeping the bikes safe and secured. So, as you see on the slide, we have specifications that we want to achieve with our system. If we look at the locking system, we're prioritizing the motor response time and the Bluetooth LE distance. The motor response time within 5 to 10 seconds so that the bike is unlocked fairly quickly. And the Bluetooth distance is also a preferred specification because we want to make sure that the user can, as they're walking up to the bike, and they can unlock the bike. For the tracking system specifically, we wanted to focus on the theft alert response time. As soon as someone attempts to cut the lock, or they successfully do cut the lock, we want the user to get a notification immediately, and the response for the buzzer as well. We want that to happen as quickly as well. So if we look at the house of quality, we can see that the primary focus of the project, in terms of the customer requirements, were reliability, efficiency, security, and quality. And as far as functionality, we wanted to make sure that to meet those requirements, we had accurate GPS, battery life was extended, and it had a good battery life, as well as the components within the system would be able to function in any type of weather. We weren't as much focused on the size and weight as we wanted to make sure that the system met the user's requirements and that they would be satisfied with uh, the features that were incorporated in the system.
Here you can see our visual design, which on the left you will see our lock enclosure, the middle the shackle, and the right the tracker. The lock enclosure has 2 slots for our shackle to sit in and 2 sliding pins as well for them to open and close, allowing the shackle to be locked. As well, on the left side is the compartment for our PCB. Then the one next to it on the right side is the battery, and the other one is for our various regulators and motor controller. On the tracker is a very open design, allowing us to fit the PCB perfectly inside and have little holes at the bottom for the speaker to be able to project the sound For our enclosure, we'll be using PETG for its high warping temperature and a good tensile strength. For our shackle, we'll be using aluminum because of its low weight and decent tensile strength. For our demo, we'll be using a plastic shackle, so it's easier for us to cut, but in reality, it would be made of aluminum, which is much more robust, making it harder for someone to steal the bike.
The Cycle Sentry hardware design consists of two main subsystems, the locking system and the tracking system, both of which work together to kind of help us achieve our goals. The locking system has multiple PCBs, starting with the main PCB itself, which houses the MCU and the BLE module for communication. Um, Moving on to the motor controller PCB, which drives the locking mechanism, and the NFC antenna and matching circuit PCB, which helps us unlock and lock the bike via NFC. Additionally, we have the 3.3 and 5-volt regulator boards, PCBs, to ensure proper power distribution across the system. The communication with the locking system is done through the BLE module, and it also uses the antenna, which also facilitates any external communication. The tracking system itself is the one that's responsible for real-time monitoring of the bike and any theft prevention. So it's all on one PCB, which includes the MCU with LTE capabilities for us to track the bike for a long range, as well as a BLE module for any short-range communication. It also includes a battery-powered alarm in case there's any tampering or anything like that. And all of these things connect to a database, which is connected to our mobile application, where the users actually interact with the lock itself through the application. The app itself provides real-time location updates, the lock status, and any alerts in the event of any tampering and things like that.
To control our two main PCBs, we first needed to choose between microcontrollers and FPGAs. While FPGAs have high performance power and scalability, our main concerns with this project were low power consumption and ease of integration. That is why for this project we have chosen to go with MCUs over FPGAs. We compared several on-the-market MCUs, and after analyzing factors like cost, power consumption, and operating temperature, as well as peripherals like Bluetooth and LTE, we chose two different MCUs. For our locking system, we have chosen to use an ESP32. This microcontroller consumes very little power and is very low cost. It has several GPIO pins and can interface with the main embedded wired communication protocols. The form factor of this chip also allows us to be able to easily solder it to the PCB. For the tracking system, we have chosen to use the Maker MB1500 from our Arduino. We have chosen this board mainly due to its built-in cellular service, allowing us to connect to the LTE network. Having LTE built into the device means not having to worry about configuring external modules, which will make the cellular tasks easier as well. It is also important to note that this board is the most expensive of the boards we compared. We do believe, however, that in this situation, reliability is everything, and paying more for this board would save us more in the long run. Given that this board is also built by Arduino, there is a vast ecosystem that allows us to integrate with existing libraries seamlessly, making it the best solution for the task of tracking.
For our locking mechanism, we considered different types of motors. For our needs, stepper motors fit the bill due to its high durability and small size so that can fit into our custom lock. For our stepper motor, we compared three different sizes, NEMA 8, 17, and 23. The NEMA 8 was the best due to its small size, lowest current rating, and lowest weight. To pair the NEMA 8 stepper motor, we also require a stepper motor driver. Between the four drives, we picked the TMC2208 since it gives us the ability for 1/256 microsteps, allowing us to have the max control for our locking mechanism.
For our NFC controller, we chose the Adafruit PN532 due to its cost effectiveness, multiple interface options, and compatibility with our system. It supports UART, SPI, and I2C, allowing flexibility in communication with the ESP32. While its data transfer rate is lower than other options, it is sufficient for our use case. The integrated antenna simplifies implementation, and its 3.3 volt to 5 volt operating range ensures compatibility with our hardware. Most importantly, at 92 cents, it is significantly more affordable than alternatives like the Seed Studio NFC Shield and DF Robot Gravity Module, making it the best choice for our budget without sacrificing essential functionality.
Since our tracking system will also have an alarm system, some sort of sound device is necessary to produce a loud enough sound to not only deter a thief in progress, but also alert others nearby of the potential robbery. While speakers are more dynamic, meaning they have better audio quality and frequency range, they also can consume a lot of power and for our application would more or less be overkill. For these reasons, we have chosen to use buzzers as they can provide enough volume as speakers can with better size and cost as well as better power consumption. While there are many different buzzers on the market, sound pressure level ratings are one of the key considerations when picking the right buzzer. However, many buzzers compared here and on the market do not provide a very high SPL for 5 volts. Luckily, after browsing online for a while, we came across the 2429 TWT from PUI Audio. At a rating of 98 dB at 5 volts, this buzzer will be able to provide just enough volume outside so that anyone in a close enough range to the bicycle will be able to hear it. Since LTE is built into the MakerBoard, that leaves finding a module for Bluetooth. After research, we found 4 popular BLE boards. After comparing factors like interfacing, ease of integration, and cost, we decided on the HM10. The HM10 is a very popular board for BLE and can easily be interfaced with using UART or SPI. The module also has non-volatile memory, meaning setup is not required every time the board receives power. For this application, we believe the HM10 is perfect for allowing communication between the ESP32 and the tracker.
For our tracking system, we selected the U-Blox SAM M8Q due to its high sensitivity, low power consumption, and straightforward integration. It supports both UART and I2C interfaces, making it flexible for communication with our microcontroller. While the Adafruit Ultimate GPS is a viable option, it only offers standard GPS accuracy, whereas the SAM M8Q provides better sensitivity for improved tracking.
In this slide, you can see different components that make up our systems and their voltage, current, and power requirements. On the left, we have the tracking system, and on the right, we have the locking system. Please note that these values are due to change since not all the components will draw max power all the time. For example, our motor will only draw power when the user requests to unlock and lock the shackle. Knowing our power requirements, we can now select a battery. To keep things simple, both systems will use the same battery. For our selection, we chose lithium-ion batteries, since it's a smaller battery, has a higher efficiency, and a low discharge rate when not in use. From there, we selected the 3.7 10,000 milliamp hour battery due to it having the longest capacity and allowing the user to use our product for longer periods of time. For our locking system, we required 2 different voltage regulators, a 3.3 buck converter to drop the voltage from 5 volt to 3.3, and a boost regulator for the 3.7 to 5 volt. The most important factors for selecting each regulator was its efficiency, size, and component total. The reason behind these factors, we wanted a regulator that's easy to solder, lowest component total to keep the complexity down, and the efficiency so we get the best power. From there, we selected the TPS 613221 and the MT3068. In this slide, you can see the block diagram of our locking system, from the 3.7 battery, the charger, 5 volt regulator, motor controller, motor, MCU, 3.3 regulator, and the NFC. In this slide, you can see the overall schematics from the ESP32, motor controller, UART bridge, buck converter for the ESP32, NFC controller, 5 volt boost converter, NFC antenna, the 3.3 buck converter, and the USB port. It should be noted that we are using the AMS1117 voltage regulator, which is usually found on the ESP32 dev board. Here you can see our main locking PCB, which comprises the ESP32 or PN532 and the various components required to program the ESP32. In this slide, you can see our motor controller and NFC antenna PCBs. Both are separated on their own boards so we can fine-tune each board independently, or if we run in the case where our stepper driver burns out, we are able to replace the board completely without damaging our main PCB. To cap off the locking system PCBs, we have the 3.3 and the 5 volt regulators, as well on separate boards, so that, as similar to the motor driver, if they burn out, we can replace the PCBs without messing up our main PCB.
Here is a simplified block diagram for the hardware of the tracking system. We can see that the 3.7 volt lithium battery will be connected directly to the MakerBoard, making it simple for powering the board and easy for us to monitor. The microcontroller will power and control the Bluetooth module, the GPS module, and the buzzer simultaneously. The overall schematic for the tracking system can be seen here. On the top left, we have the pin headers for the MakerBoard, and to the left of that, there is a voltage divider allowing us the ability to measure the life of the battery, which is connected to the board directly. On the top right, we can see a simple circuit used for the buzzer alarm. On the bottom left is the HM10 module, which we are connecting through UART, and on the bottom right is the Sarah M8Q, which we are connecting through I2C. This is the PCB layout of the tracking system. The MKR developer board can be placed directly onto the PCB, allowing for ease of operation. The HM10 can be seen in the upper left-hand corner, the buzzer in the right, and the GPS module at the bottom. The battery plugs directly into the JST connector located on the MKR developer board.
So for our purposes, for the wired communication protocols, UR and I2C are the best ones. Given that UR and I2C use fewer wires than compared to SPI, it's easier to implement the communication between the microcontrollers and the other peripheral devices. Most of our models are easily configurable to either using UR or I2C. allowing us to pick whichever protocol is easier to program and implement.
For our short-range communication with the bike lock, we chose NFC. NFC is the better choice for our smart bike lock due to its short range, security, and smartphone integration. With a 10 centimeter range, NFC ensures only the owner can unlock the bike, unlike RFID, which operates up to 100 meters and is more vulnerable to unauthorized access. NFC is also cheaper, more intuitive, and consumes less power, which makes it ideal for a battery-powered lock. Most importantly, NFC works with smartphones, enabling seamless unlocking without extra hardware. These factors make NFC the best fit for Sentry's security and ease of use.
As mentioned earlier, long-range communication is important for a project like this, as the two systems need to be able to talk wirelessly with each other as well as send information to the database. For internal communication between the devices, we have chosen to use Bluetooth Low Energy, as it is a fast protocol with very little power consumption, even less than standard Bluetooth. While devices still need to be relatively close in order for communication to happen, this is okay for us since if the two devices are not close to each other, it's more than likely someone has stolen the bike anyways. Discussed earlier as well, we have chosen to use LTE-M. This protocol runs on the same framework as LTE, allowing for easy integration between the two. Using LTE-M allows us to not only send and receive data from the database, but also allows us to send notifications to the user, alerting them of a robbery in progress.
For our tracking system, GPS was the best choice due to its global coverage and high accuracy, making it ideal for outdoor bike tracking. While WPS, also known as Wi-Fi Positioning System, is cost-effective, it relies on Wi-Fi network availability, which is unreliable in outdoor environments. BLE can be used for short-range tracking, but requires a dense deployment of beacons, making it impractical for our use case.
So for the software design, there are a few features that we're going to be implementing or that we've implemented. First is the NFC authentication. Then we have the tampering detection, the GPS tracking, and the user notification. Most simplest is the NFC authentication. If the correct NFC tag is used, then the lock itself is unlocked. Whereas if there's if the lock is cut or anything like that, then there's a much more involved process, and we'll kind of dive a little bit more deeper into that when we discuss the bike lock activity diagram. So as you can see on the bike lock system case diagram, the system to lock and unlock for the user is much more simpler than the case states for the robber itself. The reasoning behind this is that the NFC tag will actually make things a lot simpler, at least for the controls. For the thieves or the robbers, there's a much more involved process since more information needs to go to the user, such as the the message that goes to the user and the location of the bike. The alarm system is also activated on the bike itself, but with the messaging and GPS coordinates, they both need to use the cell towers to communicate back to the database and then to the user itself. And then the GPS needs to communicate with the satellite and then the cell tower and then the user. So it's a much more involved process. To simplify things, though, if we look at the bike lock activity diagram, it kind of highlights each stage of the lock. So it shows how the components would be integrated with another to kind of produce the response that we want. So the user would first request to unlock the bike that's attached to the bike. And to do that, they would use the NFC tag. The reader would then authenticate the NFC tag, and if it's successful, there wouldn't be any other action that's required. The bike lock would be unlocked, and the system would return back to normal, waiting for the next request. However, if there are multiple failed attempts, then there are multiple states that the system would go through. And so the first is that the system would communicate to the tracker and it would turn the alarm on. Once the alarm is on, there'd be a push notification that would be sent to the user on the application where they would see that the bike lock has been tampered with. As well as the GPS coordinates, they would also be transmitted to the user. And this will help the user track where their bike is in real time. And once all of these steps have been completed, the system would then return to idle mode.
For our IDE, we chose the Arduino IDE because of its ease of use, native support for both ESP32 and Arduino MKR1500, and its extensive library ecosystem. Unlike other IDEs, Arduino IDE has a large collection of pre-existing libraries, making development faster and more efficient. Leveraging these well-documented and optimized libraries ensures a stable and reliable communication system. For our database selection, we chose Firebase because of its real-time capabilities ease of mobile integration, and low maintenance, making it ideal for IoT applications. Unlike MongoDB, which is better suited for bulk data storage and retrieval, Firebase operates as a real-time database, allowing instant synchronization of bike stats, GPS location, and alerts across devices. This ensures that users receive updates immediately when their bike is locked, unlocked, or tampered with. For our mobile app software, we chose Dunkable because of its ease of use, built-in Firebase integration, and real-time testing capabilities. Unlike Flutter and Xcode, which require extensive coding, Dunkable allows for fast prototyping with pre-built components, making it ideal for IoT applications. Dunkable's seamless Firebase integration ensures smooth communication between the lock and mobile app, making it the best choice for our project. Here are some screenshots from our mobile app that we've been developing, which we have a login screen, lock status page, location tracking, and settings.
So for our hardware and software testing, if we first start with the hardware, the voltage regulators that we're using, the 3.3 volt and 5 volt regulators, we tested before connecting them to the board. We tested using an electronic load, and we used a range of 0 amps to zero point 0.5 amps, and zero point 0.5 amps is the max amount of current that we'll be drawing from those voltage regulators, and they were able to provide us with the proper readings. So for the 3.3, at max, it provided us 3.3 volts, and for the 5 volt at max, current draw it provided us with 5.1 volts as the output. For the motor controller, we can see in the image on the slide that whenever the motor controller was activated, it produced a response on the oscillator, and so that's how we knew that the motor controller was working when we first tested it. For the NFC card, we wrote a small program that would allow us to see the UID of the tag. When we first wrote the code and tested it out, we were able to get the UID value, and that's the value that we use to then authenticate the user. For the GPS, when we were testing it, we weren't able to get a precise reading from inside the senior design lab. We had to go outside to get a better reading, and we can see that in the image on the slide as well. So for some of the hardware challenges, for the lock, the first thing that we had a problem with is that the 5 volt regulator wasn't boosting to the correct voltage, and so we realized that there was an issue with the surface mount inductor, and so we changed it to surface mount inductor to a power inductor from the MT3608 development board. The serial communication success rate for the programming was about 90%. And so for us to get an accurate transmission rate, we added the missing pull down resistors to the serial lines, something that we missed uh, while working on the schematic. Another thing for the lock, another challenge that we had was that the reset and boot push buttons weren't working. And so we added smaller debouncing capacitors to those buttons. So they are now functioning properly. And then lastly, for the tracker, the GPS module at first wasn't receiving any power. And so we found that there was an accidental wire trace in one of the layers that caused a short in the connection. So we cut the trace, and then we were able to get power back to the GPS. As far as the software challenges, starting with the lock, the biggest thing for us was that the NFC library would freeze the ESP32, causing the other tasks like Bluetooth to not be um, used simultaneously. So whenever we wanted to either use Bluetooth to unlock or connect to the device, it wouldn't allow us to because the NFC would constantly be scanning for a tag to unlock the bike. And so the proposed solution for that, which we did implement, was that we use free RTOS, which is the scheduler separating the NFC and Bluetooth tasks, and so that they can run simultaneously. As far as for the tracker, because we implemented a schedule or the scheduler for the different tasks, there were some issues that would interrupt the LTE modem, so it wouldn't allow us to properly connect at times. And so the solution was that we created flags that don't allow the scheduler to continue while the modem is active. So it basically put it on pause. For the application itself, the Bluetooth connection would sometimes work on some devices, but not on all devices. So we just needed to reconfigure the entire connection within the application, and that's how we solved that problem. For the tracker, the alarm, because it was in a different task, in its own task, it would randomly turn on even if it wasn't called or activated. And that was just because the scheduler, the way that it was scheduled and prioritized within the code, it didn't allow any other tasks to be performed while it was operating. And so we just set a lower priority to the alarm so that the other tasks can execute. And there was an additional function that was written so that that task would only execute whenever it entered, whenever that function was called.
Our budget for this project is roughly $800. Most of that money has gone towards the PCB and electrical side of things, as the cost of the main hardware and multiple PCBs have added up very quickly. About $200 has gone to the batteries, charging protection, voltage regulators, and other things related to the power supplies. We gave ourselves a lot of wiggle room here in case there were issues like burnt regulators or damaged boards. For making the enclosures, we gave ourselves an $80 limit as to allow for multiple 3D printing iterations for both testing and practical use. We also set a limit of $40 for cellular provider bills, but we have not gone over this budget since it costs 3 cents per megabyte of outgoing data. For our work distribution, this is a simplified table describing each other's role in this project. For hardware, Andres and I have been in charge of the PCB designs, where Andres has focused more on the locking system and power distribution, and I have worked more on the tracking system as well as the wireless communication integration. Derek and Russell have been working on the software side, where Derek has mainly been working on the locking system, motor controls, and the Bluetooth connection, and Russell has been working more on the tracking system, mobile app development, and the database. Thank you for watching our final presentation for Sentry. We hope you found something interesting about our design and project. Take care.